Assalamu alaikum students. Today's topic is going to be about physical optics and we'll solve its numericals. Let us look at the first numerical. It says, in a young double slit experiment, the separation of the slit is 1 millimeter. Let's assume that we have the young double slit experiment over here, and these are the two slits, and the distance between the two slits, according to the question, is 1 millimeter. So this is our D. A red light and a red light of wavelength 620 nanometers is falling on it. That means light comes in the form of wavelength, enters into the slits, and then goes onto the screen. So now the wavelength is 620 nanometers. Determine the distance between the center bright band and the fifth bright fringe on the screen. So if this is the screen and this is the center part, let's call it O, then 1, 2, 3, 4, fifth fringe we have to find out. And what is the distance between the fifth fringe and the center part? The screen which is 3 meters away from the slit. One thing more is given to us. The distance between the screen and the slit is 3 meters, which is represented by L. The distance between the fifth fringe or bright fringe and the center part, we call it Y. So let us look at the data for this question. The separation between the screw slit is 1 millimeter. So we convert the millimeter into 10 to the power minus 3. The wavelength of red light is lambda, which is 620 nanometers, or we can say 620 into 10 to the power minus 9 meters. For fifth fringe, we can say n or m is equal to 5, because this is the fifth fringe he's talking about. Distance between the slit on the screen is basically L, which is represented by 3 meters. Distance of the fifth bright fringe from the center of the screen, we are calling it Y5. So this is Y5. So here we have the solution. The formula for the Young double slit experiment, which says Y is equal to n lambda L divided by D. So here Y is Y5. N is the number of fringes which we have, which are fifth fringe. So we have N also. The distance D is 3 meters. Oh, sorry, 1 millimeter. And we have the value of L as well, which is 3 meters. Now putting in the values from the above equation, what do we get? Let us put in the values. We get 5 into 10 into 620 into 10 to the power minus 9 into 3 divided by 1 into the power minus 3, or we can say 1 millimeter. So when we calculate this one, we get 9.3 into 10 to the power minus 3, or we can say instead of writing 10 to the power minus 3, we can write it down as 9.3 millimeters. So this is our answer of the first question. Moving on to the second question, which says two parallel slits are illuminated by light of two wavelengths, one of which is 5.8 into 10 to the power minus 7 meters on the screen. The fourth dark line is of a known wavelength coinciding with the fifth bright line of the light of the unknown wavelength. So one is known and the other one is unknown. Find the unknown wavelength. We have to find the wavelength of the unknown. Now we have the situation over here. Here's the screen. Here are two slits. Here's the center part. Now in this case, we assume that fourth, 1, 2, 3, and fourth of dark fringe of one light, which is of a known wavelength, because on the screen, fourth dark line of the known wavelength. That means let us represent the red line is of the unknown wavelength, which is coming from here. And the fifth bright fringe of the light of the unknown wavelength, and we have to figure it out. 1, 2, 3, 4, and 5. 5 fringe of the unknown bright light. Now, these are the two cases which we have, and we want to find out the wavelength of the blue light which is coming from here. Now, let us look at the data. The wavelength of the first light lambda is given to us, which is 5.8 into 10 to the power minus 7. The fourth fringe is basically third one in this case. So of the dark fringe, so it will be 1, 2, and 3. Wavelength of the second light, which is lambda 2, which we have to find out, which is of the fifth fringe, which we can see over here. And solution. The position of the dark fringe. Where was the dark fringe? The dark fringe has a formula y dark is equal to m plus half. Why we have done the half? Because whenever we are solving for the dark, it must be in the half lambda, and when we are discussing with the bright light, it must be in a whole lambda, so that we can represent in a dark or bright fringe. So as it is dark, so m is 3 for the dark fringe. So m plus half lambda 1 L divided by d, because L over d are the same, because the distance between the slit and the screen is same, and the distance between the two slits is also the same. The dark fringe can be written as of the fourth dark fringe, it is 3 plus half, because it was the third one bright fringe which was closer to this one. So 3 plus half, because third plus half of this one, as you can see from here, will give us the fourth fringe, the dark fringe. So 3 plus half lambda 1 L over d. So let us take the LCM of this one. So 3 plus 2, 1 over 2. So let us take the LCM. It will be 6 divided by 2 plus 1 divided by 2. So if we solve this one, we'll get 6 plus 1 divided by 2, or 7 over 2. So this is what I've done over here. Put 6 plus 1 divided by 2. Now, when we got to this point, that we got after solving this one, 6 plus 1 is equal to 7 over 2, as we got over here. Now, we call it equation number 1. That means we have found the fringe for the fourth value for dark fringe. It is 7 over 2 lambda 1 L over d. Now for the bright fringe. Now in this case, position of the bright fringe, we already have the value of m, and m is equal to 5. Only we have to put in the value of m. So y bright is equal to m lambda 2 L divided by d. So for m is equal to 5 for bright fringe. So let us put the value of m is equal to 5. So y bright will be equal to 5 into lambda 2 L divided by d. Now this is the equation for the bright fringe. Now let us compare these two equations. To find out the value of the unknown, we can find out the value from the known of the unknown. So according to the given condition, let me clear that out so that you can see this one. So according to the given condition, fourth dark light of the first light of the unknown of the known wavelength coincide with the fifth bright line of the light of the unknown wavelength. That means these two lines, that in blue and red, they both were coinciding on the same line. So the distance was same. Now in this case, the fourth y, that means the distance from here to here, will be the same. Y will be the same. So that is why y dark 4 is equal to bright y 5. Putting in the values of equation number 1 and equation number 2, we get 7 over 2 lambda 1 L divided by d is equal to 5 into 2 lambda 2 L divided by d. So this L divided by D and L divided by D cancel out with each other. We already have the value of 1 lambda, which is the value of the known wavelength, which is 5.8 into 10 to the power minus 7 meters. So let us put the value of lambda 1 in this one. We get lambda 2 is equal to 7 over 2 lambda 1 divided by 5. So we just have rearranged this equation and we have written the value of lambda 1 in this case. By solving this one, we can get the value of lambda 2. Let us put in the values and see what is the answer. Lambda 2 will be equal to 4.1 into 10 to the power minus 7 meters. So that is the wavelength which is of basically the red color, which is moving from here to here, which was unknown, and that unknown value is turned out to be of fifth bright fringe of the blue color actually. So this is the unknown color which we have, which is 4.1 into 10 to the power minus 7 meters. Moving on to question number 3, it says when the movable mirror of Michelson interferometer is moved 0.1 millimeters, how may dark fringes pass through the reference point? If the light of the wavelength is 518 nanometers is used. Now in Michelson interferometer we have a situation like this, that we have two mirrors like this and mirrors in situation like this. One is movable, the other one is not movable or non-movable. Let's call this one non-movable and this is movable, or we can say fixed. So here's the source and here's the telescope, and we can see through this telescope. So in the first case, let me draw in such a case that the first light comes over here, it bends, then passes from here, then bends again, reflects back, goes back over here. Let me clear this out. It comes back from here, then from here, and then reflects back and goes into the eye. For the other situation, we have a second wavelength, which is moving from here, which is orange line. It reflects from here, goes to the non or movable mirror, reflects back, and goes into the eye. So these are the two situations of Michelson interferometer. So he says that if it is moved, this movable mirror is moved 0.1 nanometers, that how many dark fringes will appear on this point of the wavelength, which is 518 nanometers. Let us look at the data first now. The distance moved by a movable mirror is 0.1 millimeter, or we can say 0.1 into 10 to the power minus 3 meters. The wavelength of light is lambda, which is 580 nanometers, or we can say 580 10 to the power minus 9 meters. The number of fringes is m. We have to find that one and the solution. Now we have the formula for this one. The formula says P, that means that the distance which we have to find out, P is equal to m lambda over 2. So what is the value of m? We have to find by rearranging this equation. So m will be equal to 2p divided by lambda. Now p was the distance moved by the mirrors, that means 0.1 meters. So this is p. Let us put in the values and find the value of m. So let us put in the values. We get 2 into 0.1 into 10 to the power minus 3 divided by 580 into 10 to the power minus 9. So this is the formula for Michelson interferometer. By simply rearranging the values and putting the values of the data, we got the value of m, which is 345 fringes. That means how many fringes which will be seen in this case? We'll see 345 fringes in this case. Moving on to this fourth question, it says a slope film has a reflective index of 1.4. Let's say that we have two layers of let's say soap and air particles. So if the light comes, it will reflect from here, and another light will come and it will take a longer path from here. Now in this situation, it says how thick must be the film if it appears black. Now in this situation, we have to find the thickness of the film, how much thick a film, or you can say a soap film, should be, so that the light which is reflecting back from here should appear black when mercury light of wavelength 546.1 nanometer falls on it normally. Now if a wavelength of 546.1 nanometers falls on it, basically it transfers from one material to another material, then it reflects back from here to here, so it has to cover a distance of 2D. So we have to cover a distance of 2D and then look at it now. Now, in this case, we have the reflective index, which is 1.4. The wavelength of light is given to us, which is of mercury wavelength, mercury light wavelength, which is 546 nanometers, or we can say 10 to the power minus 9 meters. The thickness of the film, let's call it X. We have to find this one, and it is 2D. That means it has to travel double the distance after reflecting back into the same medium. The first order M, we have to find out. The solution is given to us, and the value of M, because it is of first order. The formula of destructive interference. Now, why it is destructive interference? Because it is reflecting from a hard surface. So whenever the light basically strikes a hard surface, its phase will change. So whenever it hits, its phase will change. And if it is like this, then after reflection, its reflection will be a phase change of 180 degrees. So it will always be a destructive interference. So as it has to travel 2x, that means the distance from here to here was x, or 2D, then it has to travel a distance of 2 x in this case. So 2nx is equal to m lambda. This is the formula for the light travel through a thin film or a soap film, we can say. Now in this case, we have to find the value of this x. So we take the value of x on one side and put all the other values on the other side. So x will be equal to m lambda divided by 2n. Let us put in the values. So the value of m is 1. So 1 multiplied by anything is 1, the number itself. And the lambda which is given to us is 546.1 into 10 to the power minus 9, and we divide it by 2n, and the value of the reflective index which is given to us is 1.4, which is in this formula. After putting in the values in the formula, what do we get? We get x value, that means the distance between the two edges of the two mediums, that means from here to here, between the two edges of the thin film, is 1.95 into 10 to the power minus 7 meters. So x is equal to 1.95 into 10 to the power minus 7 meters. Question number 5 says a diffraction grating has 5,000 lines per centimeter. Let's say if we assume to be a lens and it has a grating, that means small slits in it, that is 5,000 lines per centimeter. That means in 1 centimeter there are 5,000 slits in that one. At what angle does the second order, that means the second order has to be given to us, spectrum of sodium yellow light of wavelength which is 589 nanometers occurs? That means we have to find out what angle is there. We have to find the value of theta, then at what angle basically the spectrum of yellow light will occur. So let us look at the data. The number of lines is 5,000 lines per centimeter. So if we convert the lines into meters, then we have to divide it by 100. And if we have to divide it by 100, then this will be written as 5,000 into 10 into 100 lines per meter, or n is equal to 5 into 10 to the power 5 lines per meter. So this is the number of you can say lines or slits per meter. The grating element is D, which is the inverse of number of lines. So we divide it by 1 divided by n. So it will be D is equal to 5 into 10 to the power 5, which will be equal to 2 into 10 to the power minus 6. So the value of D, the distance between the slits, any two slits, for a single slit, we can say the distance between any two single slits is 2 into 10 to the power minus 6 meters. And we have the second order. So M is equal to 2. The wavelength is given to us, which is 589 nanometers, or 589 into 10 to the power minus 9 meters. We have to find the angle theta. So here we have the formula and the solution for the differential equation is d sine theta is equal to m lambda. So by rearranging the equation, what do we get? Sine theta is equal to m lambda divided by d, or we can say theta is equal, or we can put in the values. We can say sine theta is equal to 200 into 589 into 10 to the power minus 9 divided by 2 into 10 to the power minus 6. We get sine theta is equal to 0.589. If we want to find out the value of theta, we have to take the sine to the other side. So it will become sine inverse. So theta is equal to sine inverse 0.589. We get the value of 36 degrees. That means the slits must be at the angle of 36 degrees, we can say, to get the values of the second order of the spectrum. Moving on to the sixth question, it says light is incident normally on a grating which has 250 lines per millimeter. That means again, this is the situation of the grating, and that means the number of slits are there, and in 1 millimeter there are 250 lines or slits, you can say. Find the wavelength of the spectral line for which the deviation in the second order. So the m value is 2, and theta is also given, which is 12 degrees. And we have to find the value of lambda because we have to find the wavelength. Now the procedure is same, the formula is same, but now we have to divide it by 1000 instead of 100. So here's the data for us. So it is number of line is not 5000 now, it is 250. Instead of centimeter, we have millimeters. So in the next case, we divided by, instead of 1000, we divided by, instead of 100, we divided by 1000. So 250 lines per 1000, we get to get meters now. So in this case, it will be 250 into, instead of 100, we get 1000. So we get in the end 2.5 into 10 to the power 5 lines per meter, and this is our required answer, that this much lines were in that much meters. That means 2.5 into 10 to the power 5 lines were in 1 meter of the distance. Now if we want to find out the distance between any two slits, that means the value of d, what we have to do, we have to divide it by 1. So the grating element is d, which is 1 divided by n. If we divide it by 1, what do we get? We get 4 into 10 to the power minus 6. So the distance between any two slits is basically 4.0 into 10 to the power minus 6 meters. So that is the d value, or the difference between the slits. And theta is also given to us, which is 12 degrees. And as it is of second order given in the question, so m is equal to 2. Lambda we have to find out. We have the formula of the differential grating equation, which is d sine theta is equal to m lambda. So taking m to the other side, we get d sine theta divided by m. Putting in the values, what do we get? We get d is equal to 4 into 10 to the power minus 6 sine 12 divided by 2. Let us put in the values and find out the answer. Sine 12 is equal to 0.2079. And after solving this one, we'll get the value of lambda, which is 4158 into 10 to the power minus 10 meters. This is the wavelength which we'll get in the diffraction grating of the second order. Moving on to the seventh question, it says, in a certain X-ray diffraction, the experiment, the first order, that means m is equal to 1, is observed at the angle of 5 degrees for a crystal plane species of 2.8 into 10 power 10. Now, what is the wavelength X-rays use? Now, this is the situation of X-ray diffraction. So this is the crystal. Let's say these are the molecules or atoms, you can say, and the wavelength is of we have to find the wavelength. So in this case, it says the wavelength comes, strike this one atom, and then reflects back. And in the same process, another wavelength comes, strike this other molecule, and then reflects back. This wavelength has to cover an extra distance, which is d sine theta. And in the same way, again, it has to cover an extra distance over here, which is d sine theta. So the total distance over here is 2d sine theta. Now, it says in the question, it is the first order image observed, and it is a bright image. So it is of a lambda, that means it is a whole number, that means it is a constructive interference at the end. So data which is given to us is first order, m is equal to first, and this says that lambda is going to be the whole number because it says it is a first order image observed. That means the lambda is a whole. That means whenever the lambda is whole, that means the image is bright. The angle of diffraction is 5 degrees. The crystal spacing, that means the distance between the two crystals, is d, which is 2.8 into 10 to the power minus 10. The wavelength of X-rays, we have to find out what is the lambda over here. So we can use the formula very simply according to the Bragg's law, which is 2d sine theta is equal to m lambda, and we got the 2d sine theta from this whole situation. This much distance and this much distance should be considered in order to find out the extra distance covered by the let's say the other line or other light actually. So we have to find the lambda. Lambda is equal to 2d sine theta divided by m. Putting in the values, we get 2 into 2.8 into 10 to the power minus 10 sine 5 divided by 1. We get, after taking the sign of 5, we get 2 into 2 into 2.8 into 10 to the power minus 10 into 0.087 divided by 1. So here is the value of lambda. That means this is the lambda which is striking the crystal plane. We can solve it by the Bragg's law, which is 0.488 into 10 to the power minus 10 meters. So this is the wavelength of that X-ray. Or we can say, in other words, rounding it off, it is going to be 0.49 into 10 to the power minus 10 meters, rounding it off. Moving on to question number 8, it says an X-ray beam of wavelength 0.48 into 10 to the power 10 meters is used to get Bragg's reflection from a crystal at an angle of 20 degrees for first order maximum. So here's the clue for us. M is equal to be 1. What are the possible layer spacing which gives rise to the maximum? That means we have to find the value of D. The situation is the same. The atoms of the crystal are arranged. The wavelength comes, it strikes the atom, it reflects back. Let's call it first wavelength. The other wavelength comes, it strikes the other atom, it reflects back, and it is making a whole lambda. So m lambda is over here. So it also has to cover an extra distance, let's say this one, and this whole thing is basically d, which is the distance between any two crystal spacing. So this much distance basically is d sine theta, and this much spacing is d sine theta as well. So as it is the first order, so we can write down the value 2d sine theta. So it will be written as 2d sine theta is equal to m lambda. So again, the Bragg's law has been used in this question, and from here we can find out the value of d very simply. So look at the data over here. The wavelength is given to us, which is of the X-ray 0.48 into 10 to the power minus 10 meters. The angle of refraction is 20 degrees. That means this much angle is 20 degrees over here. For the first order maximum, m is equal to 1. The crystal spacing is d. We have to find that one. So solution, so 2d sine theta m lambda. So here we are. D is equal to m lambda divided by 2d sine theta. Putting in the values, what do we get? M is equal to 1, and lambda is equal to 0.48 into 10 to the power minus 10. 2 into sine theta, which is 20 degrees, is 0.342. What do we get at the end? D is equal to 0.70 into 10 to the power minus 10 meters. So the D, that means the distance between, which is over here actually, the distance between the two spacing or crystal spacing is basically 0.7 into 10 to the power minus 10 meters. Then question number 10, it says the spacing of one set of crystal planes in an NaCl salt table is D is equal to 0.282 nanometers. That means if this is the molecules over here, again, and a wavelength, let's say it comes from here, it strikes and goes back, and another wavelength comes and strike the other molecule, or you can say plane, and strikes, and it has to cover an extra distance. Let's say with a blue color, this much distance is extra from here, so it will be d sine theta in this case, because this is theta, and the similar way this is theta, so this much distance is d sine theta. So as in the question, it says the monochromatic beam of X-ray produces a maximum, Bragg's maximum. Okay, so it is maximum, so lambda is going to be a whole number when it's glanced at the angle of plane is 7 degrees. That means this theta is equal to 7 degrees. Assuming that it is a first order maximum, that means n or m, you can say d sine, actually the whole case from here to here, the whole distance, this much distance is 2d sine theta is equal to m lambda, because it is the first order, so m is equal to 1 or n is equal to 1. We have to find the wavelength of the X-rays, so we have to find lambda in this case. We have the data now. The order is maximum, or m or n, you can say, is equal to 1. The crystal inner plane placing is d, which is 0.282 into 10 to the power minus 9, or you can say nanometers. The angle theta is 7 degrees. Wavelength we have to find out. We have the formula, which is 2d sine theta, m lambda, or you can say n lambda. In this case, it is going to be 1. So let me clear this out. Now, if we put in the values to find the value of lambda, it will be 2d sine theta divided by n, and n is equal to 1. So 2 into 0.282 into 10 to the power minus 9 into sine of 7. So if we solve this one, we get the value of lambda. That means the wavelength which is coming over here, which is 6.9 into 10 to the power minus 11 meters. Or we can round it off to 0.069 into 10 to the power minus 9 meters, or we can say lambda is equal to 0.069 nanometers, because it is 10 to the power minus 9. I hope you understand today's lecture. Inshallah, we'll continue next time. Until then, bye bye.